Welcome to Textbook Engineering Problem, where we explore complex engineering problems and discuss different methods for solving them. In this video, I'll be breaking down a problem and discussing different ways to tackle it. However, keep in mind that there is no one correct path for some of these solutions, and I encourage you to share your own insights and thoughts in the comments. Together, we can learn and improve our problem-solving skills. So, sit back, grab a notebook, and let's dive into today's problem. Today we're working out of Elementary Principles of Chemical Processes 3rd edition, and we're doing problem number 3.28. I'll read the problem statement. A 5.00 weight percent aqueous sulfuric acid solution with a density equals 1.03 grams per milliliter flows through a 45 meter long pipe with a 6.0 centimeter diameter at a rate of 87 liters per minute. Okay, let's write down all of the stuff that they've given to us here. Okay, I've written down all the stuff that they gave to us. They gave to us that the weight percent of acid is 0.05, and the rest of it is water. There's a volumetric flow rate of 87 liters per minute. The density of the solution is 1.03 grams per milliliter. The length of the pipe is 45 meters, and the diameter of the pipe is 6.0 centimeters. And then from the back of the book, we can get the molar mass of sulfuric acid and the molar mass of water. Okay, let's look at our first part. Part A, what is the molarity of sulfuric acid in the solution? So molarity is a measurement of concentration, and it specifically refers to the moles of whatever solute you're using. In this case, we're using sulfuric acid per liter of solution. So moles of sulfuric acid per liter of solution, that's molarity. So in order to calculate molarity, we need to know the number of moles of sulfuric acid in the solution of a certain volume. Okay, in order to calculate this, what I'm going to do is take a sample of this solution that is 100 grams. So I took a 100 gram sample, and now I'm going to analyze my 100 gram sample. Okay, so first I'm going to look at how many moles of sulfuric acid are in my 100 gram sample. Well, I have a certain mass of sulfuric acid in my 100 gram sample, and I know how much that is because I have the weight percent of sulfuric acid. So I have my mass of sulfuric acid, and I'm dividing that by the molar mass of sulfuric acid in order to calculate the total number of moles of sulfuric acid in my sample. Next, we need to calculate the volume of solution we have. The volume of solution in a 100 gram sample is equal to the mass of the sample divided by the density of the sample. So I have a 100 gram sample. I'm dividing that by 1.03 grams per milliliter, and I get a certain number of liters of sample. Now I have the number of moles in my sample, and I have the volume of my sample, and so now I can calculate what the molarity is. The molarity of my sample is equal to the number of moles of sulfuric acid divided by the volume of the solution, and that equals 0.25 moles per liter. Alright, that's it for part A. For part B, it asks how long in seconds would it take to fill a 55-gallon drum, and how much sulfuric acid, in pounds mass, would the drum contain? You should arrive at your answers with two-dimensional equations. Alright, for part B, the function that we want to look at is the volumetric flow rate with respect to a time increment. So if we have a certain amount of time of a volumetric flow rate, if we multiply those together, then we'll get a certain volume. If we want to know how much time to fill a certain volume with a flow rate, then we can just rearrange that equation. Rearrange this equation to solve for time instead. And then we're given all of the following information. It's a 55-gallon drum. This is our flow rate, and then we just do the unit conversions to change from gallons to liters and from minutes to seconds. And we're left with 140 seconds. how much sulfuric acid would the drum contain? In this case, we're looking for a mass of sulfuric acid. Well, it's lucky that we just calculated what the concentration of sulfuric acid was in the stream, because now we can take the volumetric amount that's in the barrel and we can multiply that by the concentration, and we'll arrive at a certain mass of solute. So we just have to do the proper unit conversions. All right, here we have 55 gallons in the drum. This is our molarity that we just calculated. And then we do the unit conversions, liters to gallons. And because this is in moles, we have to change it into mass because it asked for pounds mass. And then from grams into pounds mass. And we're left with 24 pounds mass sulfuric acid in the drum. All right, for part C, it says the mean velocity of a fluid in a pipe equals the volumetric flow rate divided by the cross-sectional area normal to the direction of flow. Use this information to estimate how long, in seconds, it takes the solution to flow from the pipe inlet to the outlet. All right, so if we assume that we have a full pipe the whole way, then we need to look at the different flow rates like it just described. So the problem statement just said that the velocity of the solution is equal to the volumetric flow rate divided by the cross-sectional area normal to the direction of flow. If we want to know how long something is going to take, like we did before, we need to look at the distance that something is traveling divided by the velocity. So in this case, we have the velocity of the flow rate, which is a distance per time, and then you divide the total distance divided by the rate, which is a distance per time, and you're left with the time it takes to travel that distance. Okay, so what distance is the fluid traveling in this case? Well, the fluid is traveling the length of the pipe. Well, what is our velocity in the pipe? Well, we just were told what that was. It was the volumetric flow rate divided by the cross-sectional area. So let's substitute that into this equation. And finally, what is the cross-sectional area of the pipe? The cross-sectional area of the pipe is in the shape of a circle, and so in order to calculate the cross-sectional area, we need to know the formula for calculating the area of a circle, which is pi times r squared. But they didn't give us the radius, they gave us the diameter of the pipe. And so we divide the diameter by 2, that gives us the radius, and then we square that, and so that is equal to pi times the diameter of the pipe squared divided by 4. And let's substitute that into our equation. And we finally arrived at what the total time it would take for the solution to travel from one pipe to the other, and we put it in terms of variables that we know. We know the length of the pipe, we know pi, we know the diameter of the pipe, and we know the volumetric flow rate. So now we just have to substitute in the values of all of these things and make sure that all the dimensions are the same. So we'll do dimensional corrections to fill in this equation, and then we should be left with time in seconds it takes to flow from one end of the pipe to the other. Here's the dimensional analysis. This is the length divided by 4 times pi. This is the diameter of the pipe squared. This is the volumetric flow rate. Then we do a correction for the centimeters squared, put it into meters. We change these liters into meters, and then we change the minutes into seconds, and we're left with 28 seconds to flow from one end of the pipe to the other. And that is it for problem number 3.28. Thank you for watching, and I hope you found this video helpful in your problem-solving journey. Remember, there are other routes you can take to arrive at the same correct answer, and I encourage you to leave a comment with any additional insights or questions you may have. Also, if you have any specific engineering problems you would like me to cover, please let me know in the comments. Your feedback is valuable, and I look forward to continuing the conversation with you. Don't forget to like and subscribe for more engineering problem-solving videos. Thanks again, and I'll see you in the next video.